Good afternoon. Today's topic, we will discuss the PID controller. We will go on overview on the PID controller. What does PID mean? P for proportional, which is a constant, I for integrator, integral, D for derivative. So I would say P as a constant Kp, I as 1 over S, derivative S. We know that in Laplace transformation, times S or 1 over S, the integrator, and Kp like as a constant. When we discussed before previous lectures, the steady state error, so we used to say here's a constant K, then here's the planet G of S, then we do the feedback. After that, when we do the feedback, we said that depending on the planets or G of S, if it is type 0, type 1, type 2, and this here is regarding to the input, there is a ramp inputs, step first, step inputs, then there is ramp, then there's parabolic. So it depends on the order. If it's step 1 over 1 plus Kp, that's the steady state error. If it is ramp infinity, if it is parabolic infinity, then for type 1, it is 0, 1 over Kv, infinity 0, 0, 1 over Ka. Do you remember that table? So basically, the overall idea, when we use only K alone won't impact, it won't impact the system type. And we already discussed root locus and the rough fluid stability to determine the range of K to keep the system stable. However, when we will add I controller. So I controller, what's going to do? It will increase the system type. If we have a system type 0, then when we add an I controller, it will make it type 1's system. Therefore, in type 1, for example, type 1 system, the input in type 1, or when we have a step inputs, it will be, the steady state error will be 0. Therefore, we will say PI controller can eliminate the steady state error. However, the derivative will improve the transient response, but it won't impact the system type. So the derivative controller will not impact the system type. So the cases of PID controller, we will discuss the several cases, like the first case, P controller alone. Then PI controller. Then PD controller. The last one, PID controller. Okay? So somebody can say, is there an I controller alone? No. D controller alone? No. I and D controller alone? No, there is no way. There must be a proportional controller first. So P, it's a common. P. While here, there's no I and D. There's only I, here there's D, then there's both. Those are the 4 cases for the PID controllers. When we look at the P controller, it will not impact the system type. So I would say P and PD won't impact system type. However, when we talk about PI and PID, will increase system type by 1. If you have a type 1 system, it will be type 2. If you have a type 2 or type 0, it will be type 1. PID or PI will increase the system type. It's very important. PID or PI, both of them will increase the system type. Therefore, whenever we have a step inputs for a type 0 system, it will improve it. Therefore, it will eliminate the steady state error. What's the impact of D? D will improve the system, what's called the transient or the performance, the transient, which is the steady state, the overshoots, will try to reduce it. That's the thing. While the I will do what? Increase the system, reduce the steady states error, or we'll make it eliminate it, make it zero. Then the other thing, which is the D controller, has a drawback, which is sometimes can impact the system stability, and it's very sensitive to noise. When you have anything, environment filled out with noise, then therefore it will fail. So again, the PID controller, it's the general applicability in most control systems. The vast majority of the control systems, the basic control systems, using PID controller. So PID controller, it will be very common word when you go to, for example, like to the industry, when you go to any other parts. What's the type of the controller? PID. So it's very important for you to know that. And this is why we studied all of the control class. This is the control. Here is the control, which is performing the closed loop system. The mathematical model, or the one of the good thing about the PID controller, if we don't know the mathematical model, PID can be very useful. What does it mean? PID controller can be designed into two ways. The first way, by knowing the system model, you just model the system, find the transfer function for that. Then what you're going to do, you will perform the PID controller using some equations, router, weighted step, Ziegler-Nichols, etc. However, sometimes, in some situations, if you don't know what's inside the system, in some situations that by trial and error, you have this system, and you don't know the mathematical model for it. We need to control it. The advantage of the PID, that's why the PID is very famous. This is the system, has inputs and outputs. What's inside the system? It's a box. I don't know. What should I do? Do the closed loop, puts the PID controller here, minus, plus. You know that, right? It's a closed loop, right? What now the thing which is, I added a PID controller. PID controller, it has some internal parameters. What are these parameters? We will discuss this later in this chapter. But the good thing about it, yes, it can do the control without knowing what's inside. Yes, it can. And it happened a lot. We did it in many applications, but not all of them. Okay, so I would say maybe you can put a system and add PID controller, but cannot control it. Yes, it can. Some systems can, some systems not. How? This you will learn this by experience. Some systems, there is no way to do that. But the good thing about it, we realized if you put the input as a step input, most likely it can do the job. If you assume the input as a step and add the PID, or if you need the input to be like step, like increasing the car speed, increasing the temperature of the air condition, these kind of small applications, it can do the job. Okay? Yeah. So in the field of the control system, it's well known that the modified PI controller have to prove their usefulness to providing satisfactory control. Although in many given situations, they may not provide optimal control. What does it mean? PID controller will not give you the faster response. It will give you a good performance, but it might not be the fastest one. It might not be the lowest overshoots. Well, sometimes we call it the optimal. Basically, the optimal means you need to have an objective, which is basically reduce the energy, reduce the time, reduce the effort. That's the optimal. But when you do the PID controller, maybe you can spend more energy. It can take more time. But at least your target can be satisfied. So the good thing about it, you can achieve your job. You can get your job done. You want to create a control system for water level tank, you can do it. If you want to do it for speed, you can do it. Air condition, you can do it. But it might not be fuel efficient. That's one of the drawbacks. But I would say sometimes I don't care. I want this job to get done as soon as possible. Or I would say get this job done without complexities. So it's interesting that more than half of the industrial controllers using PID. if you work in a company or industrial area, more than 50% of our controllers are based on PID. That's why I'm really focused. I say like it's very important for you to know PID before leaving this course. It's very important for you to understand how it's going, because you will see it. Definitely, you will see it in the future. So because PID are adjusted on site, there are different ways of PID. We can say on-site tuning, and sometimes we call it off-site tuning, or online and offline. When we do it online tuning or online design for the PID controller, you don't need to know what's inside the model. However, if you are doing offline, you need to know the internal model. Or I would say design, and based on the model, or design based on if we don't know what's inside. Okay, there are two ways. So how can we make the design? Something we call it tuning rules. There are several tuning rules, but the most important thing or the most famous thing is Ziegler decode. Okay, here are again the strategies controllers. We have PID, PD, PI, P. There's something we call on-off or big bang controller. This is something I haven't talked to you. I didn't discuss it yet. So we will discuss these. We call it 1, 2, 3, 4, 5 types of controllers. The first type, on-off. This is not P controller, not PID. It's not of these forms. What's this? This is basically the simplest formula, which it can be used in air condition. In air condition, assume that the temperature is, for example, 150 Celsius degrees. And we need to, for example, like increase the temperature. So what's on-off based? Let's assume the reference temperature is 150. Then here, the green line is the actual temperature. So what's happening? It has a certain margin. So I would say, for example, we will make the margin as plus minus 10 degrees. Come on, why it's not working? The margin plus minus 10 degrees. So what's going on in Big Bang or on-off? If the temperature goes below than 140, what's happening? The heater will start until reaching not the desired plus 10. So we will say the desired is, for example, 150. Then I would say if it reaches below than 140, on. When it's reached more than 160, off. So what's happening again? It will be turned off. Here, actually, it's already off. You see, it's off. Then it will be on. When we turn it on, what's happening? It will be increasing until reaching more than the targets. Then it will be turned off. Here is off. Okay? Then until reaching our criteria, which is 140, it will be cooling down. So turn it on, then have some rest off. It looks like when you are running, then relax. Then run, then relax. Okay? Do you think this is a good approach? It's simple, easy to implement. Yes, there is an error. The other thing, like I would say, we cannot do it in many applications. Assume that you are making a speed control. Go like this. Assume that pressing fuel, then the speed, for example, 160. Then just remove your leg from the fuel, from the accelerator. Then it will be what? Rest, then turn it on. Turn it on, turn it off. This is happening in the refrigerator. Turn it on and turn it off. This is not efficient. This is consuming a lot of energy. You can imagine, like again, assume that you want to walk from here to, for example, Bayruni. So do you prefer to walk or do you prefer to run, then relax? Run, relax. What do you think? Walk, of course. So walk, you will reach faster, right? Then the same here thing for the controllers. If you turn it on, turn it off, turn it on, turn it off, this will be consume a lot of fuel. This sometimes in some applications might not be sufficient. Here in the temperature, it can be okay, but it's not energy. Energy, it will not save the energy. Like, you know the air condition, we say we have old air condition, new air condition with inverter. Do you remember that? Do you know this? مش inverter بوفر الطاقة صح. So we said like air condition with inverter. What's the point? The old air condition are working like this. You see the temperature, then it's cooling down, then turn it on until reaching the certain thing, then turn it off, right? However, when we have with inverter, it will do continuous monitor. So what will happen in the continuous monitor? It will be like this, something like this. Which one is better? Of course, this one is better. This one will save a lot of energy. There will be no of energy consumption. However, this one will consume more energy. In some applications, it's not feasible. Assume you are driving a car, and it will not be like this. In cruise control, the car cannot be turned on, then off, on, off. This is not feasible. It's not only on, off, turning on or turning off the car. I mean also the accelerator. Take it and remove it. In accelerator, I think the human control, we are doing some. When we reach a certain speed, we will not remove our leg fully from the gas, right? Or from the accelerator. We are keep pressing. So your body is the controller, or your brain is the controller. Okay? Again, this one is used a lot on off in all electronics applications, like in 90s, in 80s, in 2000. This is in all the applications. However, nowadays, this is, we call it, it's very old, and we will not use it anymore. Or sometimes you can use it. It's simple. If you don't care about the energy, if you don't care about this thing, if you don't want to make a lot of energy consumption, or I mean, if you don't want to make a lot of complexities analysis, then you can do it. It proves its feasibility. It can be feasible, but not optimal, not the best. How about P controller? P controller, this is the closed loop. We know the closed loop, right? And we know K before. Yeah. This is P controller. So the transfer function of the P controller, G of P controller of S will be KP. Okay? This is the transfer function of the P controller. It's very important for you to memorize. Here's the transfer function. How about the impact of the P controller? The impact of the P controller is like this. Assume we want to make our desired temperature like 175. The P controller will do the heat, reaching 165. Oh, I want 175. Why we have this? Why? I put my input as what? Step. And the system is type 0. Therefore, it's what? Still steady. Exactly. So it is system type 0, right? And therefore, when we have a ramp, step input, what's happening? 1 over 1 plus K, right? So there is a steady state error, 1 over 1 plus K. Do you understand this? That's why there is a step. Can I reduce the error? If you increase the gain K, increase K, what's happening? 1 over 1. For example, plus infinity will be 1 over infinity, which is make it 0, but you cannot make it infinity K. So I would say, if you make K, for example, 1, it will be 1 over 1/2, the error. If you make K 100, it will be 1 over 101. Which one is lower? This is the error. 1 over 100, 101. So if you increase K, what's happening in the system performance? Will go something like this. Will be very close. But there must be a steady state error. You cannot solve the problem. You cannot make it infinity. That's one way. That's one thing. The other thing, sometimes when you increase K, the system will be unstable. How can I know that? You can do router with stability. Okay. So sometimes I would say, I don't have the freedom to increase K as much as I want. So maybe I can increase the gain reduce the steady state error, but I can reach to a point that there is, for example, 10 degrees steady state error, and I cannot solve it. Assume you're driving a car and you want your speed 80 kilometers per hour. Your controller will achieve only 70. This is useless. Okay. That's something that I want you to do. Therefore, I would say, as the gain increase, it will be faster, but I would say until eventually it will be unstable. Increase the K, then it will be unstable. Therefore, I would say PID controller might not be a good option. It can be fine if steady state error is okay with you. If you don't care about 150 degrees or 140, if you consider them, both of them are the same, then that's fine. You can consider this. Then the same thing here, if you consider as on office, okay, then okay, you can use it. Again, those are applications. Again, if you increase the K, it will be like this, again, K, enter reaching to that unstable range. Now, what's the other thing, which is the PI controller? The PI controller, as we said, it will increase the system type. So type 0 will no longer be 0. It will be converted to be type 1, right? Increase system type. Then since it is type 1, then when we add the step inputs, it will be what? State error. 0, exactly. That's the advantage. Therefore, if we use PI controller, we'll make the life easier. Here is how it looks like, the PI controller. Here is KP, KI. How can we write the transfer function? If we write it as in time domain, it will be like this. But the way that I like is to write it in the Laplace domain. In Laplace domain, the transfer function will be this one. KP plus KI over S. This is the transfer function of PI. Sometimes we call it GPI of S, okay? GPI of S, which means the transfer function of the PI, which is basically, you can replace this by this block, which is KP plus KI over S. Okay, does this make sense? The good thing, advantage about it on the PI controller, which is eliminates steady state error. When you have your desired value like this, something similar to the underdamped, like we did before. But there's a drawback. The drawback for that is the overshoots. Okay, assume you are in elevator, and elevator you are in floor number 0. You would like to go to floor number 1. So when you travel from floor number 0 to floor number 1, if you are using PI controller, you will feel the oscillation, the overshoot and kind of oscillation like here. Okay, so it will oscillate. Then to reach your desired. Okay. However, if you are using PID controller, what's going to happen? The oscillation will be less until almost non-oscillation. That's in modern elevators. In modern elevators, you will barely feel it, right? However, in the elevator, if you are using PID controller, assume you are using PID controller and you will travel from floor number 1 to 100. Then, because PID controller has a steady state error, it will stop at floor number 90. Do you think this is feasible? No way, of course. So that's why sometimes in elevators, PID is the best. There is something new here or something different, which is proportional derivative control. So PID controller, I would say it's very, rare. And I mean, based on my experience, I have never used PID controller. I use either PI, PID. But PD, in my point of view, it's very rare. I'm not sure about the other applications, but I would say in my field area, which is my area's power system and control, I have never used PD controller. Anyway, the PD controller will improve the system performance. However, it has a drawback because of the stability. So the PD controller, this is the proportional, this is the D controller. If we need to do it in S domain, it will be KP plus KD over S. Therefore, you can replace this box by saying it's KP plus KD over KD times S. Okay? Does this make sense? That's great. The next thing is, here's like the D controller, again, like the impact of the D controller, basically, it will try to make sure stabilize or the adjusted the performance. Let's talk about the other thing, PID. You see, here's the portion, here's PI, we have a D, PID. So PID controllers, the transfer function of it can be replaced, this box, by a small box, which is KP plus KI over S plus what? KD times S. Okay, and sometimes we will add as G of S, G of S of the PID controller. Okay, this is the transfer function. Does this make sense? So here is the transfer function, GPID, PID of S. The good thing about the PID, almost no oscillation. See? No oscillations, no oscillation, and no error. A P controller alone will make the system move from here to almost close to the steady state. P alone. I eliminates the steady error. Because overshoots. D remove the overshoots. You see, we are using the advantages of both three. The combination of these three will do the whole job. P alone will run the system. Without P, the system will not run. I will remove the states error, while D will remove the overshoots. Look at this table, you need to memorize it. Memorize it, store it in the brain. KP, if you increase it, the rise time will be decreased, the overshoot will be increased, settling time, small change, almost no effects. When we say a small change, you can say no effects. Steady state error will be decreased, but not eliminated. Decreased, not eliminated. And thus we all agree, and we are all agreeing that KP, increasing KP at a certain range will make the system unstable. Right? There's a range to make it unstable, will be unstable. KI, if you increase KI, rise time will be decreased, which make it faster. Overshoot will be increased, that's it. A drawback. Cyclic time will be increased, that's a drawback. Because system error will be eliminated. KD, small, not impact on rise time, no impact. Overshoot will be decreased, that's our target. And cyclic time will be decreased. No impact on the system error. Again, assume you have the design or the choice for elevator. What's the best controller? P, PI, PD, PID? PID, of course. Why? When we have a PID, we will not have, we don't have steady state error. We don't have overshoots. So it will be smooth from floor number 0 to 100 without a problem. However, when you are using PI alone, there will be oscillation. So when you travel, if, for example, poor design, it will go, when you go to floor 100, it will go to 102, back to 92.8, then to 101, then back to 99. So assume you have the elevator that goes up and down. This will be useless. We don't, I mean, it will be annoying. However, when you use a PID, it will remove the whole problem. Tips for designing the PID controller. Now, we are all agreed that the transfer function for the PID controllers, let me write them here. The transfer function for the P controller is what? G of S for the P controller, it's what? Come on. P, right? P controller alone. The transfer function for the PI is what? Come on, I'm sorry, KP. What's what? KP plus
AI over S.
KI over S.
Plus
How about the PD?
KP times S.
KP plus KD times S. How about PID? KP plus KI over S plus KD times S. That's one notation of using the let's call it that. What's called the PID controller. There is another transfer function representation, the same one, like this one, but with different way. This thing, we call it the theoretical. This one, the practical, that you will see when you're programming the PID controller, when you have it in real life application. Like, for example, in control system lab, we are not using this one. We are using different notation. What's the notation? Let's see. The KP, the P and the P controller is the same. KP. There is no problem with that. In PI, it's kind of different. KP, 1 plus 1 over TIS. PD, it is what? KP, 1 plus TDS. Then the PID, KP. So the thing, we put KP as a factor. 1 plus 1 over TIS plus TDS. Let's compare it with the original definition. KP, KP, there is no problem with that. While the original, the other one, it was KP plus KI over S. So what's the value of KI? KP over TIs, right? Right? The relationship. Do you agree? Okay, how about TD? Here it is, it used to be KP plus KD times S. Therefore, the relationship is what? KD equals KP times TD. Do you agree?
Yeah.
Therefore, the transformation between these two is important. You need to know how to do it. This is a relationship. Then the last thing is this one. KP plus KI over S plus KD times S. And the same formula here again. KP is the same as KP. KI equals KP divided by TI. KD equals KB times TD. Okay? All good? Now we know two representations. The practical representation or the industrial representation and the theoretical representation. Using TI, TD, and KP, this is we call a practical representation. However, this one, the theoretical representation, KP, KI, KD. Again, that table is very important for you to understand. Here, the thing now, after, okay. After we plot it, let's see, are we still? Are we still sharing the screen? Okay, anyway. When we put the PI controller in any design, PID, here is G of S, and here is the PID, right? For example, most likely if we need to do step response, that's what we will focus basically on, step response. So PID, look at the PID. We put the PID. Is it enough? Not enough. We need to know the values, right? What's the value of KI? What's the value of KP? What's the value of KD? Or what's the value of KP in the representation TD, TI? What are those values? How can we determine them? This is something we call a PID controller design. which is how to design the parameters. One of the ways, trial and error. Trial and error, just guess any value, observe. Is it going to give you a good response? It can work, trial and error, but this is not professional. In some sensitive applications, this is not acceptable at all. Maybe you can burn some devices. You can make the system unstable for some values of gains. Then you can cause some fires, which is something that we don't want. So tips for designing. Obtain the open loop response and determine what you need to be improved. That's our thing. That's the way that we are thinking. What's the system now before doing any controller? Then what do I need to do? That's how the targets, I mean, tips, which is something that keep it in mind. Then after that, let's make it a closed loop with PID controller alone. Right? Because the I controller will, what's going to do with the purpose of I controller? Eliminate state error. D, improve the states, the overshoot and the other thing, right? Which is the transient. So I would say the first or try to do the most important thing. What's the system right now with open loop? Then after that, add PID controller, open loop. Then add PID controller. Observe, there is still state error. Okay. Add integral controller. Okay, you remove the overshoots, but there is what's, I mean, remove state error, eliminated, but there is overshoot, add derivative controller. So these steps, one of the way in how to make trial and error. Trial and error. So you cannot do it randomly or the trial and error. If you use these steps, it can give you some approximated performance. It can give you maybe good performance, maybe not. It might work, it might not. But in some situations, it can work by doing trial and error, which is by guessing. يعني زي تحديد زي إجابة شيء. جرب أحط أرقام. Try like open loop. Then let's put P as 10. Then let's put D as 1. Then try like step. Put first, do it and run the system. Then add PID controller, run the system, monitor this. If, for example, like it's very high or unstable, change P, make it reduce it to make it stable. Then add D controller, add I. This is one of the trial and errors, but if you are using this, it can work. They can be okay, but it's not recommended. How can I find these values? Ziegler-Nichols. Ziegler-Nichols using, propose a method similar to this. You can use similar to this, but the way that we need to do is basically try to regulate it based on scientific approach, which is how can I add P alone? How can I observe it? How to do the Ziegler-Nichols? This will be our next lecture topic. Let me stop here and end the recording.